Hey everybody. Okay, so we're going to be talking about classifying stars today. This is the first lesson of our physical science class. So bear with me. I'm going to be trying this out for the first time, the screencasting technique. So we'll see. These are just some questions. Just think about them right now. How near is the closest star other than our sun? Is the sun brighter than any other stars, or is it just closer to us and that's why we see it brighter? What colors are stars? Are brighter stars hotter? What sizes are stars? And are most stars isolated from other stars as the sun is? Okay. Okay. So to answer some of these questions, there's something called the inverse square law. Basically, it says with greater distance from the star, the light is spread over a larger distance and the apparent brightness is less. So the reason why stars are not as bright as our sun is because the farther a star is from Earth, the dimmer it looks to us. And our sun is the closest star that's like closest to us. So it looks so bright because of that. When you double the distance, the distance actually makes the star look one-fourth as bright. So if it's double the distance from us that our sun is, it actually looks one-fourth as bright. It's only 25% as bright as our sun. And if you triple the distance, you decrease the star's brightness by a factor of 9. So that means it's a ninth as bright as our sun. So if you just kind of look at this picture, it's kind of similar. Like if your car is super close to you and only 10 meters away, like the lights are really bright. When it's 20 meters away, they're a little less bright, and 30 meters away, they like don't really look that bright at all. So when we're talking about color and temperature, stars actually come in several different colors and they come in different temperatures because of that. Temperature is linked to the color. The hottest kind of stars look blue, okay? So they have a blue color. The medium ones look orange and yellow, and the coolest stars look red. So, I mean, this is of course is like they're relatively cold, like you would still burn up if you were like in front of that star. But in comparison to the super hot stars, like a cool star is fairly red. So this right here is sort of a little key for spectral classes, color, and temperature. So I would definitely like make a note of this chart because you will use it in your project to help identify what the color and temperature of your class project star is and like what that means. So a spectral class of O means that you'll have a blue-violet star. Its temperature will be 30,000 to 50,000 Kelvin, so really, really hot. It's probably the hottest kind of stars you'll have. And the spectral lines will be ionized atoms, especially helium. So these are the elements that are in those spectral lines of the stars. And so these are just examples of stars in this column right here that fit in that category. So B is the blue-white stars, A is the white stars, F is the yellow-white stars, G is yellow stars like our sun. So our sun is in this yellow range. It's only about 5,200 to 5,900 Kelvin in temperature, which is really, really hot. To give you an idea, freezing point, I believe, is at 273 Kelvin. So, like when it's cold and it's snowing, it's like 273 Kelvin or something like that. It's, yeah, it's like 5,000 is like a lot hotter than that. Like you would burn up instantly if you got anywhere near the sun. So this right here is an HR diagram, a Hertzsprung-Russell. So these were a couple of guys that came up with this diagram, so of course they named it after themselves. An HR diagram is something that you're going to use in your project. You're going to collect an HR diagram or get like a picture like this, and then show me where your star is on that diagram, okay? And something you're going to import into your doc for the project. So just keep in mind that this is something that you're going to want to, again, get a picture of and input in your project. So basically what's going to happen is, we're looking at these stars and these are the different names of stars. So like Arcturus, for example, is here. So because it's here at this point, what that means is if you look at the bottom, you have spectral type. So it's going to tell you the spectral type. So because it's here in this orangey band, it's between a K and an M. Okay. So it's like the orangey sort of color you can see. It's like in that orange band, orange yellow. It's if you look at the absolute magnitude, that tells you like the like absolute space, like the magnitude where it is. The luminosity is how bright it is. So the higher up you go, the more bright it is. Since it's kind of in the middle, but it's brighter than our sun, which is at 1 right here, it's brighter than our sun. And the surface temperature goes to the left in terms of heat. So the right is the lower, is the cooler stuff, and to the left is hot. So Arcturus is like kind of on the low range. It's not as hot as our sun, which is a little bit to the left and is in this yellow band. So it's less than 5,000. We could say like 4,900 Kelvin. So that's just how you read an HR diagram. So here is another chart that's kind of like the HR diagram, but not. It's like it shows us the different types of stars we're dealing with. So see our reliable Arcturus right here. That's right here. It's a giant, so that means it has a certain size, and it's a type of star. We're going to talk about the life cycle of stars, and that's what this is related to. Main sequence is sort of like it's in its main sequence of life. It's like kind of like it's a young adult, like it's just sort of starting out in life. A white dwarf is like really old, like super, super old. Giants are sort of like the 40s range. Super giants are like the 50s, 60s. We're like comparing it to human age. And then white dwarfs are like, 80s or 90s or something like that. So that just kind of gives you an idea of like the path, right? And if you notice, our sun is right here. So it's kind of been hanging around for a while, like a few billion years right now. But it's still in its main sequence. It's still got a while to go. So the HR diagram shows the star brightness plotted against star spectral types, which are the color and the temperature. The brightness and the spectral type are related. Main sequence stars, which fuse helium and hydrogen to helium, fall along our red curve there. And giants are to the upper right, and supergiants are on the top. White dwarfs are below the main sequence. Okay, so this is just the basics of the HR diagram. Hot and bright goes to the top left, cool and bright goes to the top right. The sun is sort of in the middle, and of course, dim is at the bottom, and hot at the left, and cool at the right. So star size is also really important. Hotter stars are brighter than cooler stars of the same size, and bigger stars are brighter than smaller stars of the same temperature. So, if you have two stars and they're the same temperature, like they're both 5,000 Kelvin, the one that's bigger is going to be more bright. So, the brightest stars are the biggest, hottest stars. Okay, and this is just an equation that helps calculate the brightness. But again, I'm not going to make you do that math. I just want you to understand that that's how it's calculated. So if you look at the mass and the temperature versus the brightness, so remember that right here they go ahead and they mark the mass. So this is the mass of the stars in relation to our sun. So our sun is 1, and then if it's smaller, if it's less heavy, then it's going to be less than 1, and if it's heavier, then it's going to be bigger than 1. So as you notice, as we get bigger, we're going to the left, the top left. And our surface temperature, as we move to the left, it gets hotter. And then our luminosity, I'm sorry, I have a whole bunch of like people mowing outside. And then the luminosity, as we go north or go up, we're getting brighter. Okay, so each dot is a main sequence star. The dot's number is the mass, and then we have the increase from lower right to upper left. So, how near is the closest star other than our sun? Proxima Centauri is the closest star. It's about 40 trillion kilometers or 25 trillion miles away. So, I mean, we're talking like super far away. Like it takes about 4 years to reach Earth from there. So, like if you want right now, you can just turn off the lights in your house and then turn them back on, and think about how long it took for the light to like for you to recognize that the light was on, right? Now, the thing is, it's like if we were to turn on the light at Proxima Centauri and then sit at the Earth and wait to see that light, it would take 4 years for that light to get here. Okay? Because like if you were to like, for example, like sit right next to the light, and then a friend was to sit across the room, and you turn off the light and then you turn it on again. Okay? Now, if you said, okay, say see it, or like raise your hand when you see the light, like the person closest to the light is going to see it first and the person farther away is going to see it like later, right? And so basically what's happening is that light takes time to reach us. And for two people in a room, it might be like, oh, it'll be like millisecond difference. But like understand that like if a light goes on in Proxima Centauri and we like are sitting at Earth, it's going to take 4 years, 4 full years before we saw that light turn on. And that's just kind of telling you the distance. So how luminous is the sun compared with the other stars? Well, the most luminous stars are about 1,000,000 times brighter, and the least luminous stars are about 100,000 times dimmer. So, yeah, really, really like, it's kind of in the middle. It's in the middle with that. So what colors are stars? Stars are found in a wide range of colors, from red through violet, as well as white. Um, are brighter stars hotter than dimmer stars? Not necessarily. Like many brighter stars can be cooler as long as they're like bigger. They can, be brighter. Um, what sizes are stars? So stars range from more than 1,000 times our sun's diameter to less than 1/100th of the diameter. So basically, our sun is kind of in the middle, and there are stars that are much, much bigger, and there are much smaller stars too. And are most stars isolated from other stars as the sun is? No, actually, in the vicinity of our sun, 2/3 of stars are actually found in pairs or larger groups. So if you like watch Star Wars, for example, and like on Tatooine, there were like two suns, right? That's like a thing. Like in within our range, like even around our sun, they're often like solar systems with like two or more stars all hanging out together. Okay, so I'm reaching about the limit of my free screen recording thing. So I'm going to go ahead and stop here, and I'm gonna like upload the video, and then I will go ahead and do a second video of this next section in the notes. So you'll be able to pause and get started again. Okay?